everyone. Outside, dense fog, 31 degrees. Wind southeast at 13 miles an hour, and barometer at 29.70 and falling very slowly.
The heat wave that has settled over France has shattered temperature records, with the mercury reaching 41 degrees Celsius in Paris yesterday. The latest report from funeral directors indicates more than 10,000 deaths in France.
El huracán Jorge amenaza el estado de la Florida. El gobierno previene a la población.
The tropical hurricane, which has moved up the Atlantic coast during the last 2 days, is expected to affect the Grand Bank area this afternoon.
South Shore over the weekend, and life was returning to normal after the freezing rain that hit 2 weeks ago.
A major snowstorm has hit central and eastern United States, paralyzing the nation's capital. The city was buried under more than 30 centimeters of snow. The storm comes a day before the opening of an international conference on the reduction of greenhouse gases. In the opinion of most scientists, the rapid increase in greenhouse gas emissions is partly the cause of the climate change we have been witnessing all over the planet.
The natural greenhouse effect caused by water vapor, carbon dioxide, and methane is extremely beneficial. If we didn't have those greenhouse gases, the mean temperature on the planet would be minus 18 degrees. It would be absolutely unlivable. Because of these entirely natural compounds, the mean temperature is 15 degrees, which has facilitated the development of our civilizations. But what concerns us is the enhanced greenhouse effect linked to human activities.
The torrential rains have caused landslides and flooding, resulting in nearly 50,000 deaths last week in Venezuela. Over a single week, 251 liters of water per square meter have fallen.
Climate change by itself has been going on since the Earth began. So often, and you see skeptics, the so-called skeptic crowd, pick up on that and they say climate change has been with us forever. It's true. Climate has changed forever. The key question is not, will climate change in the future? Of course it will. Is what are we doing to cause climate to change? I mean, people will point to glacier, interglacier cycles, and we have a reasonably good understanding as to why that occurs, but that's entirely irrelevant as to whether or not we putting in greenhouse gases is going to change the climate in the future.
In these early days of the 21st century, climate disturbances are perceptible everywhere, and scientists are in agreement. Global warming is a reality. It's most evident in so-called at-risk regions like the Canadian Arctic, where its effects can already be observed.
In Shishmaref, Alaska, the last storm carried off 18 feet of shoreline. The mayor has requested aid from the state authorities to speed up the process of moving the village.
There are the three classical hotspots of climate variability in the world, one being the Western Arctic, that is the part of the Arctic north of Alaska and Canada, the McKenzie Valley area. The second is the Antarctic Peninsula, that tip of land that sticks up toward South America. And the third is the Siberian Arctic. And there we have reports of permafrost melting at unprecedented rates, up to 30 meters a year of coastline retreat. Now, that's enough to send shivers up any land developer's spine, and it certainly is something that is going to impact on the northern residents.
Like the inhabitants of many other northern villages, the people of Saxe Harbor on Banks Island are already feeling the impact of melting permafrost. The drainage of lakes into the sea could even deprive the community of its source of drinking water.
When I was growing up, it was quite cold all the time. As the years go by, it started to get to notice in the mid-70s that it's gradually warming up little by little. And by the 1990s, we had a very warm summer, and there was some landslides in banks and stuff like that. And also, there was one lake that drained out, and there's another one right now in the process of getting close to being drained out into the ocean there. And we're finding different species of birds that we haven't seen up here before. And also there is some salmon, a few salmon that we did run across a few years ago.
In these regions, the effect of climate change is visible. The southern boundary of the Arctic is moving northwards. Southern ecosystems with new plants and animal species like fish, birds, and insects are migrating north.
When I was a teenager, the people, they used to be able to predict the weather maybe a day or two ahead of time. But now you can't really, because it's changed so rapidly, you know.
Once again, forecasters are calling for bad weather in London. Low-pressure areas on both sides of the Atlantic will continue to bring rain. Tomorrow evening, a front from the west.
Long-term weather forecasts are now part of a sophisticated new science. To better understand the weather of tomorrow, climatologists design complex mathematical models.
For us, what defines climate in daily life is temperature, precipitation, and wind. So to start with, that's the objective of a climate model. To be able to simulate the movement of air, we have to separate it into many parallelepipeds. So we set out a grid on the planet. Then we divide up the atmosphere into a series of vertical layers. That gives us a parallelepiped within which the laws of fluid mechanics that we have set out are followed.
If you were able to step inside the climate that we simulate, you would feel weather that wasn't exactly the same as the weather outside, but weather that's pretty close. It wouldn't be a world that's entirely unfamiliar to you. So we really try to capture the short timescale variability of the system.
To ensure that a model is reliable, annual surface temperature variations from red to purple are simulated, and the geographical distribution of temperatures over the seasons is monitored. When the simulation is compared with actual measurements, the model accurately mimics reality.
When you think about the Arctic and climate, it's important to always remember that the Arctic is part of a larger climate system, and you really can't take the two apart. And it's also useful to think of the climate system as having a job to do, and that job is to deal with the excess amount of heat that comes in the equatorial and subtropical regions and transport that heat northwards or southwards to the polar regions where it can be lost back into space. And the way that that heat is transported is by the atmosphere and the ocean. And let's say that half of the work in that job is done by the atmosphere, and another half is done by ocean currents.
The polar climate is unique. It's where the planet's greatest temperature variations occur. This phenomenon is closely linked to a sunshine cycle, in which the long nights of winter give way in summer to the midnight sun. In summer, there is an explosion of life. The specialized wildlife that live here have adapted to a long period of winter ice cover and a short open water season. Ice covers 14 million square kilometers in winter. It's reduced by half in summer. However, there is increasing evidence that the ice cover is becoming permanently smaller. Over the past 40 years, it appears to have lost 40% of its volume.
flooding of the Saguenay region of Quebec was the result of excessive rainfall between July 17th and 27th. More than 2,000 millimeters of rain fell during that period, double the average for the region. Electricity and telephone services were knocked out and hundreds of houses were washed away by the floods. The authorities announced today that some 16,000 people were evacuated from their homes and 7
And once you look at all the evidence, then that you can see that there is substantial warming from the ice cores. This is from the ice cores, and you can see the warming that has been going on. It's pretty well unarguable, I think. The ice caps, ice sheets, are essentially archives of past atmospheres and temperatures. So if you drill down through it, you drill through clean snow and then last summer surface. But by hand, you could go down 20 meters of that water. That is probably snow and fern from last year. And then you take it back to the lab, and then you carefully cut it, and then melt it and analyze it. Up north, you find the dirtiest snow is in the spring, and then it cleans up a bit in the summer, and then then it starts to get dirty in the winter, then very dirty in the spring. So you get these sequences. They're almost like tree rings. In the Canadian Arctic, say in the middle of an ice cap, you drill down to bedrock, you get ice age ice at the bottom, ice from the last ice age still there. So you get a fairly good resolution record from about 11,000 years ago to the present. And surprisingly, perhaps, you find that once it came out of the ice age, very rapidly got warm, warmer than today, in fact. And it's been persistently cooling ever since, until about 150 years ago. Then a rapid kind of warming, followed by a little bit of a plateau without much warming at all. And now, since 1985, we've really gone into a warm mode. And the last warming, it shows that carbon dioxide plays a good 50% of the cause for warming. And where does that carbon dioxide come from? It's got to come from fossil fuels, obviously.
In industrialized countries, carbon dioxide emissions from burning fossil fuels comes equally from 3 sources: industrial production, motor vehicles, and domestic consumption.
This graph represents the increase in carbon dioxide content from the end of the 19th century to the end of the 21st century. Back in 1880, the content was 300 parts per million. It began increasing in the mid-20th century due to human activities. Today, carbon dioxide emissions represent 7 billion tons per year. Under this scenario, by the end of the 21st century, we'll be up to 25 billion tons of carbon dioxide a year. Obviously, that's a worst-case scenario, and we hope it won't work out that way because it makes no sense in regard to the problem we're dealing with. You have to understand that every year, the continental and oceanic biosphere absorbs between 2 and 3 billion tons of carbon. So in order to stabilize the greenhouse effect, the sources must match the sinks. This shows that there's a factor of 10 between what is emitted and what should be emitted to stabilize the level of the greenhouse effect.
Some carbon dioxide emissions are trapped and stored by forests and oceans, which therefore are considered to be carbon sinks. The Beaufort Sea, covered in ice part of the year, is bordered by the continental shelf and the polar ice cap. It receives large quantities of fresh water from the Mackenzie Delta. The study of carbon dioxide fluctuations here is of particular interest to scientists.
Well, the CASES project, CASES study, stands for Canadian Arctic Shelf Exchange Study. We're now here in the Mackenzie Shelf, Beaufort Sea area, so we're interested in understanding better the impact of climate and mostly sea ice variability and change on the exchanges of carbon from the shelf to the deep basin, and also through the biological processes that are omnipresent in this very complex system. So the originality of CASES is that it's not a mono-specific study, it's a very, very multidisciplinary, multi-country study, over 10 countries involved. And from viruses to whales, people on this ship are watching every step of the ecosystem. We've got biologists, biochemists, physical oceanographers. So it's a very complete program that's trying to actually set the basis of these processes.
The first stage of this in-depth study is to measure atmospheric exchanges. What enters the air and the dynamics of the gases that circulate there. Any alterations in atmospheric exchange can have a significant impact on the Arctic ecosystem's natural cycles.
One of the reasons why the Arctic is particularly sensitive is that a small change in temperature can lead to a very large change in conditions, especially close to the freezing point of seawater. If Arctic temperatures decrease a little, then it means there will be more ice. The ice reflects more sunlight, making the surface cooler, and so there's a positive feedback there. Equally well, if the Arctic warms up a little, and it doesn't have to be all year, but warming up in the springtime or warming up in the autumn when the ice is either forming or melting is important. If there's warming, the ice will melt sooner or form later. Now, when the ice is not there, the dark ocean absorbs a lot more solar radiations, and that solar radiation warms the ocean. Yes, if it warms, it will continue to warm.
Well, what happens in the central Canadian Arctic basin? Sea ice is formed in the fall. As you drop the temperatures down, the ocean will freeze at about -1, -1.8. And when you start to form that ice, it caps the ocean from the atmosphere. That's the most significant thing that sea ice does, is it slows down the movement of energy from the ocean to the atmosphere. As soon as that ice cover is solid and formed, then the air will cool off considerably. Now, that first-year ice at the end of a season, if it doesn't completely melt, it will stay on through the summer melt period, and it'll become what we call multi-year sea ice. And as it survives those summers, of course, it gets progressively thicker and thicker and thicker as you go through the season. The way the ice circulation works in this area here is it'll get caught in a gyre, and that gyre circulates with time, and it'll just continue to cycle around the Arctic. Ultimately, though, what happens is that ice will eventually be flushed out through Fram Strait into the North Atlantic, and there it will melt.
The Arctic has a distinctive system of currents, a cardiovascular system. Water masses from the Atlantic and the Pacific follow complex routes around basins before emerging in the Atlantic, along the Labrador coast and the eastern coast of Greenland. There they meet up with warm, salty water carried by the Gulf Stream, which is part of the great ocean current system that encircles the planet. In this region, large water masses of different densities collide continuously, pushing the colder waters towards the ocean floor and setting convection currents in motion. this contributes to climate control. As it moves north, the Gulf Stream disperses some of its heat into the northern hemisphere. Without this, Western Europe would have a Siberian climate. But if the temperature and quantity of fresh water from the Arctic Ocean were to change, this crucial cycle would be disrupted. A predicted slower current would result in a major climatic variation.
It's impossible to give clear and simple pictures about how the Earth is going to respond to these changes in the patterns. However, when we build our society and we build our agriculture and our economics expecting things are not going to change, we're making a big mistake.
Je suis heureux de vous accueillir à Idriss.
Oui, d'autant plus que pour moi, c'est la première fois que je viens ici. En fait, les chercheurs...
To try to understand how the planet will respond, scientists are using climate models that require an astronomical number of mathematical operations to integrate ever more numerous variables. Even supercomputers have to grind away for nearly a year to simulate a century of climate change.
These machines, this group of 3 machines here, are vectorial supercomputers. They produce around 300 billion instructions or operations per second, and they run 24 hours a day, 365 days a year.
The projected distribution of temperature changes for 2050 shows that polar regions will be affected to a much greater degree than tropical regions.
Right now, the models predict that sea ice may become seasonally absent as early as 2050, which means that there would be no ice cover in the summertime. That has very far-reaching effects because it would mean that the weather in the northern hemisphere would change because the atmosphere would be getting a lot of energy from the ocean throughout the year. But it would also change the oceans because the oceans would be receiving a lot of solar radiation that it wouldn't normally get. It would have very far-reaching consequences, and nobody is really sure exactly what would happen in that kind of a scenario. One of the main reasons we put so much effort and emphasis into doing the detailed research work on sea ice is exactly for that reason. We need to understand that now so that we can make reasonable predictions about what the future holds.
We always think of the Arctic as a desert. It's not a desert. While it's ice-covered and snow-covered, yes, the light cannot penetrate the water column. There's other life forms. There's heterotroph. There's other life forms. But the big bloom comes in the summer. But when it comes, it's very important. It's drastic. So if you would put the quantity of biomass produced in a month in the Arctic, it may be the equivalent of what's produced in a year in the tropic.
In the Arctic, everything is linked to a distinctive light cycle. Marine organisms have adapted to a very short but extremely productive summer. Because the food chain contains only a few links, energy is transferred to the top of the chain very efficiently, from diatoms to copepods to small fish like Arctic cod, to seal, and lastly, to the polar bear.
Polar bears only feed when there is ice. They feed in the summer to some extent, but it's only supplementary. And in order to feed properly, to gain weight to allow them to survive through the year, they have to have a platform of ice because their principal food is the ringed seal. And without ice, they can't hunt seals. Not really. They have to hunt seals through the ice where the seal is at its breathing hole. So the ice is essential for them in that sense. Well, this population here and the James Bay population to the south are the southernmost polar bears in the world. And it could be argued that they have found a sort of a balance here that is very fragile.
In the summer, the bears don't eat. When they come off the pack ice in July, unless they find a dead beluga whale or a dead caribou, or they're not actively eating unless they find something that they can scavenge on. They are totally dependent on their fat reserves to survive through the summer. So if they have a shorter period of time to build up the fat reserves over the course of the winter when the pack ice is there, obviously it will affect their ability to survive through the summer.
In recent years, it has been observed that the ice has been forming later than traditionally. Something like 2 weeks later, on average, over recent years. The ice at the same time is leaving the bay. The freeze-up is occurring sooner. And it's been observed this is something like 2 weeks as well. The problem in that is mostly related to the emerging females with young, because the bears who go onto the bay to feed in November time are able to feed from then until July. And so for there to be 2 weeks less of feeding, it isn't a good thing, but it's a little bit more manageable. However, the female who emerges with her young in March and April, she only has about 4 months or slightly less in which to feed. So to remove 2 weeks from that, to have the ice leave the bay 2 weeks sooner, is to reduce her feeding period by something like 15%. And that is very significant. And if that was to continue in the future, as it may, is going to possibly leave these animals with an inadequate amount of time to feed themselves and their young and to get them through the period of the summer when they don't eat.
If the models are accurate and the ice cap does disappear around 2050, it's highly probable that a number of species of marine organisms, including mammals, that depend on ice will disappear as well. What will happen to underwater life forms like ice algae that have evolved to live under the ice. We know very little about the current Arctic marine ecosystem, how it evolved, and how variability in the physical environment affects its biodiversity. This makes it difficult to predict what will happen if the ice cover disappears. In this multi-layered marine ecosystem, scientists analyze the varying biochemistry of the water column at different depths. They are just beginning basic research on viruses and bacteria.
Our first step is to take samples from different layers within the ocean. And basically what we're trying to do is to understand the structure and the functioning of this ecosystem. How does this ecosystem work? And how will it change in the future? How has it changed in the past in response to variations in climate? And a lot of the life that we work on isn't immediately obvious. It requires very special sorts of techniques to penetrate deeper. In fact, it's really only been the last few years that we've had the tools that are really necessary to go beneath the surface of the ocean and ask the question, what is the species diversity in this incredible environment? And what we're seeing in the process of this work is an extraordinary richness, an unbelievable richness at all levels. It's extraordinary that here we are in the 21st century, we still don't have names for the most of the species, most of the biomass that exists out in the world ocean. So one of the central questions is how much of the carbon is made available to the rest of the food web and how much is lost? What are the sinks of carbon in this ecosystem? We know that some of the carbon is respired, is utilized by these very small life forms. We really need to understand that balance between these different processes in order to be able to predict the carbon flows and the energy fluxes in the future. The absence of an ice cap changes everything in terms of the structure of this environment, the nature of the habitats for the life forms in this environment. There will be a change in species, without a doubt. There will be losers and there will be winners in that change. Already we are seeing in the northern part of the Arctic the loss of complete ecosystems, ice-based ecosystems, for example, that are disappearing. Ancient ice systems dating several thousand years have collapsed by in excess of 50 or 60, 70%. There are certain sorts of ecosystems that will no longer be part of the Arctic environment. These in turn will be replaced by other sorts of organisms, other life forms.
Scientists are just beginning to understand the role of oceans in atmospheric carbon fluctuations. Current research is making it possible to develop better climate models that may be able to predict the true winners and losers of the coming change.
It's an ecosystem that's tuned to the timing of the ice, to the timing of breakup, to the timing of freeze up, to the extent All of these things are going to be impacted, and they're going to be changed. And by looking at models and trends and observations, we can get an idea of what is possible. Now, we take those to the policymakers and say, this is our view of possible futures, and what are you going to do about it?
The state of emergency was still in effect in Prague today, following the worst flooding of the century. Makeshift barriers were erected to...
We're now in an energy crisis, and that's why I decided to not have mandatory caps on CO2. We'll be working with our allies to reduce greenhouse gases, but I will not accept a plan that'll harm our economy and hurt American workers.
And this shows you the projected change in surface temperature, year for year change in surface temperature, incrementing 1 year at a time. And the clock will keep ticking until you reach 2100. You see that gradually the whole surface of the Earth becomes warmer. These red colors indicate warmer temperatures.
Models predict temperature changes that resemble what the Earth experienced during the end of the last glaciation.
Under this scenario, the mean temperature on the planet would increase by 3.5 degrees, unevenly distributed. The largest warming would occur on the continents where we live. For example, in Europe, 4 to 6 degrees. Moscow would have the temperature of Paris, and Paris the temperature of Algiers. These are really major climate changes that will have visible consequences in our regions too. We believe the first visible consequence is that half the alpine glaciers will disappear.
The glaciers, wherever they are, they have a thing like a bank balance almost. And snow falls on them, and of course it falls from top to the bottom in the winter. And then when the summer comes around, what you get is that the snow at the top stays. And lower down, the snow melts, and if it melts more than it accumulates, then you've got a negative balance over a period of time. And in the Canadian Arctic, there's no doubt the last 25 years, the glaciers are getting more and more negative.
But what's going on a global scale is that glaciers are melting. Almost all the glaciers in the Arctic region we know are melting, and that water is now being freed up and is going into the oceans. It's actually one of the things that complicates shoreline erosion here, is that the ocean level is rising, but it's rising because glaciers are melting, not because sea ice is melting. But also, as you warm the planet up, you increase the ocean levels simply by expansion. You warm the water up and it expands larger. You combine those two kinds of things with less sea ice in a region, and if you look at the ocean here in the Mackenzie Shelf area, the other problem with shoreline erosion is because there's less ice in this area, when the wind blows, you get larger waves, and those waves travel further inshore and have more energy and can, of course, erode the landmass more efficiently than it would have otherwise. So coastal erosion, of course, has many impacts on local communities, and the situation here in Tuk is particularly problematic because of the community that's located here. They have difficulty maintaining the landmass for the housing, as well as the infrastructure for sewage and electrical and those types of things.
The ocean has incredible inertia, which means that since thermal expansion affects the entire ocean, it will continue inexorably. If it's 50 centimeters at the end of the century, it'll still be 50 centimeters at the end of the next century. But the thing is, from the moment the sea warms up by around 5 degrees around Greenland, we're afraid the Greenland ice sheet will partially melt. And the disappearance of half the ice sheet would provoke a sea level rise of 3 meters. Between that and thermal expansion, the sea level could rise by 5 or 6 meters. Not in the 21st century, but let's say in the 23rd or 24th. But if we get to the end of the 21st century and we're still in that position, it will be almost inexorable. I believe we don't have the right to do that.
Projecting future climate for 20 years from now, for example, turns out that those projections are not very sensitive to the scenario that you use for greenhouse gas emissions over the next 20 years, because much of the warming that will occur over the next 20 years will be the result of past emissions of greenhouse gases. So that's something that climatologists call the committed warming. So we've already made a commitment to future warming by changing the composition of the atmosphere. The climate system presently is not in equilibrium with that changed composition of the atmosphere. And so even if we don't change the greenhouse gas composition of the atmosphere, if we manage to stabilize the atmosphere composition, the climate will still try to come into equilibrium with those changed conditions.
The idea that the Arctic is all part of a global climate system has to always be kept in mind. And by being part of a system, it means if you push on it, it may push back. It may react to what you do. And there have been 3 ideas put forward whereby the Arctic may respond by shutdown of the ocean conveyor belt or a modification of it. Another is a change of the albedo of sea ice, and a third that isn't getting too much attention but could be potentially very serious is the release of carbon dioxide and methane, which is also a greenhouse gas, from the permafrost and from the methane hydrate layer that's buried deep in the Arctic soils. This is a different part of the carbon cycle that biological oceanographers study. They're looking at the fast carbon cycle, what grows this year, what recycles through the food chain. Now we're talking about carbon products that have been stored in the planet for millions of years that are being maybe released catastrophically in one big burp, if you like, into the atmosphere and then compound the consequences of greenhouse gas warming.
There's many projections, and they're beginning to become more, which suggest that in a climate that is warmer than today, one should expect more frequent extreme precipitation events. That is, a shift in the so-called distribution of precipitation events to be such that there will be more extreme events.
Forest fires rage. Northern Europe has been hit by torrential rains. In several cities, the heavy rains and violent winds of recent days have paralyzed transportation and economic activity.
Let's say a more variable climate, more extreme. That would be seen, if nowhere else, in insurance policies. The real problem is not the average climate, although that's a problem too. It's the variability. We fear greater variability. For the moment, we don't have proof, but the risk of a warmer climate would be more storms, more tornadoes, more adverse effects on infrastructures and our daily life.
Climate change models are helping us to see our home, planet Earth, in new ways. We now realize that the natural balance is changing, and it's clear that we are playing a role in the changes we are witnessing today and are forecasting for tomorrow. The question is, How can we survive these changes?
And what we need to do, of course, is if we want to reduce emissions, we have to get to levels significantly below. More than 50% globally, that's including India, China, etc., are less than 1990 levels. And that has to happen very rapidly. And then we'll stabilize our levels of greenhouse gases at 4 times pre-industrial. That's a level that hasn't been seen since the dinosaurs roamed the earth.
I have a clock on my desk that has a little polar bear going around in the water, and it reminds me that time is passing. We do need to begin preparation. We have to do things to keep what we have, and I just hope that my grandchildren don't look at my clock on my desk and say, "What's that white bear going around in there?" Well, to be confident of our future, we have to act now. There's a saying that in the absence of new information, decisions will be based on the assumption that things will not change. Policy will go on as if we live in a frozen world. And the one thing that we know is that climate variability is real, and it's large, and it has gone on since the Earth became a planet. We have to, every one of us, put whatever talent we have, make whatever effort we're able to do to prepare for inevitable change.
From Singapore to Manila, everyone's wearing anti-pollution masks, while in Indonesia, forest fires continue to rage.
As far as the future of the planet's concerned, I still think that one of the things that isn't emphasized enough is population growth, and consequently using so much energy. And once that's gotten control of, then things may go better, but it's going to be a rough ride, I think, a really rough ride for over 50 years, maybe 100 years more.
2 large wildfires covering 187,000 acres were 2 miles apart and drawing closer Thursday in southwestern Oregon, with 17,000 more residents warned they may have to evacuate with only half an hour's notice. The state has already battled more than a dozen fires, all starting by lightning, that have burned some 350,000 acres in the state.
We must remain optimistic because this is only one of the problems facing our planet. I hope we'll succeed, but our entire mindset must be changed in terms of energy production, energy consumption, and travel. We must take responsibility. The only way, as far as we're concerned, to face up to our responsibility is to start right away with concrete measures. They may not be particularly effective at first, but the only way, for example, to influence developing countries is to impose constraints on ourselves.
Factories in northern Italy's industrial heartland are attempting to return to normal after the floods that have devastated the region. It is the country's farmers who appear to have suffered the most in the disaster.
Climate change certainly is a global problem, but it's a global problem that hasn't been created by everyone in the globe. That is, the industrialized world is the world that has created the problem, and the problem has no bounds, though, of course, where its impacts are felt. So I think there's a great onus on developed world to assist those in the developing world through the transfer of clean technologies, through the assistance in their methods for adaptation to the consequences of climate change. But we must show leadership because the problem was caused by us, and the solutions will also have to be made and given by us as well. So in fact, I think a lot of people don't realize that there is a great link between the climate change issue and the global security issue. When you have a problem created in one part that has consequences in others, that sows seeds for discontent.
Not a drop of rain has fallen in over 5 weeks. The drought has lasted so long it has deprived cattle farmers of much of their fodder and caused production to drop. Farmers are keeping an anxious eye on the barometer.
Today, we are experiencing climate change that is extremely rapid by historical standards, and scientists are predicting a cascade of upheavals with devastating effects. The Arctic is like a frontier outpost that helps us recognize the scope of what is happening early on. In the history of evolution, species have always adapted to climate variations by moving from one region to another. Tomorrow, where will the species of the Arctic go?